Well, how are you doing? Okay, this is going to be hopefully a quick video on the nonsense that is spherical excess. Okay, I'm going to explain what it is and show how false it is. Right. Excuse, you might hear a little bit of background noise. I'm not in the normal place I record. Okay, here in front of us, you can see a diagram of a theodolite. Okay, you have obviously here this dial here for your horizontal angles, and if you come down here, they'll have an azimuth dial for their for your vertical angles, and down here the azimuth dial for the horizontal angles. So theodolites, they measure vertical and horizontal angles, right? So the azimuth angle will look like this, and let's just say they'll measure, let's say, 10 degrees north northeast, or sorry, north northeast on the dial here over to 50, then they know that's 40 degrees, right? So there you go. It's simple, right? Pretty straightforward. And this will be horizontal, and they have levels on them to make sure it's absolutely horizontal. So there's no messing around. So this will be absolutely vertical, and this is absolutely horizontal, right? Simple stuff, right? Easy to learn, easy to, maybe not easy to master, but easy to understand. Okay, here's a triangle. In surveying, right? In surveying, what they do is they will have the length of one of the sides, and they will then use the angles to determine the length of the other two sides. Okay, that's how they do it in surveying. So when they are creating a triangle for triangulation or whatever in surveying, they're doing it from one point. They're not taking an angle here, then taking an angle there, and then taking an angle here, and adding them all up. That's not what they're doing, right? They're going to be taking an angle. If this is on a mountain here, they'll know the distance between this mountain and this mountain, and they'll take this angle here, and there's another mountain over here, and they'll work out the full area in between those three mountains, right? Using straight lines. That's what they'll be using. You can't look through a theodolite, right, or an auto level. Not that they use auto levels for this, but you can't look through either of those and have a curved line. It doesn't work. You can only see in straight lines. That's how we see things. Everything is in a straight line. There's no such thing as curved light or curved lines of sight or any other rubbish like that. So that's how they do it. They won't be going to three different places and taking three different angles, then adding them up, because that's complete nonsense. They'll take one angle, right? They'll take an angle from one part and know the length of one side, let's just say, right? Now, they'll expand on that as well, because they're not just adhere. Within the triangle, they'll have to adhere to 180 degrees, right? They have to. It's going to, for a triangle to be real, then it has to have 180 degrees exactly. But they can do quadrilateration. Sorry, I'll show you that in a minute. Where they'll have another triangle, maybe here and over here, and they'll have a series of triangles, and that's how they'll work the survey over a distance. But if you're talking about geodetic surveyors, they're going to be doing it from mountain to mountain, as opposed to on roadways or big construction sites, railways. That's more planar surveyors, right? But planar surveyors and geodetic surveyors are doing the exact same thing. There's no difference, absolutely no difference whatsoever. My mother's partner is a retired geodetic surveyor, and I went through all the things he used to do, and he used triangles 180 degrees. We were never using spherical triangles, none of this carry on, none of this stupid nonsense. Like everything he did, he went through what he did, how he did it from mountain to mountain. I talked to the man about it. That's how you do it. you can't do triangulation with a triangle that has curved lines and more than 180 degrees, because it's not a triangle then. These things, you can't do that. It's impossible. But obviously people out there think it's possible. But that's because there's a lot of rubbish out there that is unfortunately part of surveying. that they put out a lot of rubbish that is not real. And I'm going to show you some of that now in a minute. Okay, triangulation. This is from surveying methods. Right. The I can't read that up there. Surveying and mapping. The ASLIC Committee on Surveying and Mapping. Sorry. So, triangulation is a surveying method that measures the angles in a triangle formed by 3 survey control points. Using trigonometry and the measured length of just one side, the other distance in the triangle, the other distances in the triangle are calculated. The shape of the triangle is important as there is a lot of inaccuracy in a long skinny triangle, but one with base angles of about 45 degrees is ideal, right? So they're using triangles. This is trigonometry, right? Triangles, 180 degrees. There's no other way to do trigonometry, right? And triangulate for triangulation, it's impossible, right? 180 degrees. Now we go to what they see. This is, I'd say, the way they're putting in the difference between plane surveying and geodetic surveying. See, this is how they're creating these claimed spherical triangles. So one of the ways that they're actually created from a center point mathematically of the sphere. But this is one of the ways they create them, right? Is via circles being created on the surface of that, what they call great circles on the surface of their sphere. And where 3 of these intersect, you get this, right? Which is what they want to call a spherical triangle, which is an oxymoron, because you can't have a triangle that's more or less than 180 degrees, and it certainly can't have curved lines. Over here you can see the actual triangle, right, before it's placed onto, let's just say before it's placed onto a convex surface. So we show you this a little bit better. Here you have it again. So you see these 3 points, 1, 2, 3. These 3 points are all equal, right? What I mean by that is the planar triangle and this claimed curved triangle nonsense. All these 3 points are meeting. And what this shows, this claimed spherical triangle, what this shows is that if you took this triangle here, this actual triangle, and placed it onto a convex surface, what happens is it bows out the lines, right? So if I go to here, you'll see it better. Excuse me. So here you can see that this triangle, when placed onto a convex surface, will cause the straight lines to bend, and you will end up with, you can't not end up with, right, if you were to measure these triangles, more than 180 degrees, because you've increased the area within the triangle, right? You've increased the area. So when you increase that area, right, this, if you can see these 3 lines, that is what's known as spherical excess. Because what you're doing at that point is you're taking reality, which is the actual triangle, and you're increasing the area within the lines of that triangle, right? So you're essentially, when they do this, this is purely mathematical. None of this happens in reality. In reality, as I showed earlier, they just use actual triangles. They can't use anything but actual triangles. But within their mathematical begging the question, right, fallacies that they have to entertain for their belief, what happens then is that they end up with a situation where they have a greater amount of internal area within their curved triangle, right, oxymoron, than is actually there in reality. So if this is a real triangle measured by surveyors between 3 mountains, and they then try and add, right, and this is an important part, the R value, right? Because for this to be real, they first, any of this stuff here, and this is why you will never find any of these as a measurement, because any of this stuff here requires first for the Earth to be measured as a globe, and it has never been measured as a globe. There is no R value measurement for a globe Earth. It doesn't exist. This is the problem. There's no measurement or system of measurement that measures a sphere. That measures the Earth, as a sphere. There is a system of measurement for a sphere, but there's no system of measurement that measures the Earth as a sphere. It just doesn't exist, full stop. But they require it to exist for their claimed great circles to exist, and then for their claimed spherical triangles to exist, so then they can claim their spherical excess. But as I showed, what spherical excess is an adding of surface area that doesn't exist, right? So what did they do about that? Now, you see, this is really funny. Watch this, right? This is from a surveying site. It's called Civil Planets, right? Right, methods of surveying. They go through plane surveying, right here, where they go through all what they do in plane surveying, where they create these like five-sided pentagons, and this is like this is all using triangles within it. Blah blah blah. I'll show you some of that again in a minute. Some more of that in a minute. But the point is that in plane surveying, this is what they're doing. They're doing reality, right? Now they're doing the same thing in geodetic surveying. They're using the same tools, doing the same thing, right? But they try and give the impression that they're not, right? If we come down to here, we have geodetic surveying, right? And I added up these three angles here earlier, right? And they came to slightly less than 180 degrees. I did the same with these three angles of this triangle, and they came to slightly less than 180 degrees, and the same for this one, slightly less than 180 degrees. So why did they have actual triangles here with angles written inside of them that is less than 180 degrees? Why would they do that? Right? For a start, it's impossible for a real triangle to have less or more than 180 degrees, number one. Number two, their claimed spherical triangle, right, has to have more than 180 degrees. So how are they fitting this into reality? These three are real triangles, right? Those angles inside them are faults, right? This is purely mathematical from geodetic surveying. What they're doing is they're taking these real triangles, they're claiming that they have angles that amount to less than 180 degrees, then they're claiming to place them onto a sphere, right? And the spherical excess makes up the little bit. This is all mathematical. None of this happens in reality outside of maths. But the spherical excess makes up the little bit that they're lacking. This is the joke that is geodetic surveying. Because when they're actually out there with the tool surveying, they're using actual triangles. These are actual triangles, these three here, right? But yet, the internal angles, if you add them up, they don't come to 180 degrees. They're slightly less. And as we know, as we just saw, right, the internal angles of a triangle placed onto a convex surface will always be more than 180 degrees, right? So what they're doing is they're using actual triangles and claiming there's less than 180 degrees in it, inside them, from what I can see here, so they can then claim that when they place them onto a convex surface, right, of just the right size, right, that they will then, that excess amount that's created will make up the little bit that they're lacking here. Now, if that is not the biggest joke ever, I don't know what is. What a farce. But that's what they're at. But let's move on, right, because I don't want to keep it going too long. I'm sure you get the gist. Here's what happens in real, right? These are chain of triangles used in surveying, right? These are all different locations, and they're using triangles like this to basically survey large areas. It doesn't matter if it's planar surveying or geodetic surveying. It doesn't matter how large the area is or how small the area is, the same process is happening. No matter what's happening, it's the same process. They have to use real triangles with 180 degrees. Right? As I said, my mother's partner is a retired surveyor. He's in his 70s now, he's very old. But he is a retired surveyor. He came into it and he was surveying before there was a lot of technology that's in there now. So he had to do all the maths himself. And his maths, there was never once he ever did anything involving a triangle that didn't have exactly 180 degrees. That just didn't happen because he was dealing with reality. So regardless of what nonsense sites like this and mathematical surveying nonsense that some of these people or groups want to get up to, regardless of any of that, right, and regardless of this nonsense, right, in reality, they had to do this, This is what they have to do. Here's more of it. Braced quadrilaterals. Braced quadrilaterals. I can't say it at the moment. But this is impossible without all those triangles having internal angles of 180 degrees. Absolutely impossible. They can't have 179 point blah blah blah. They have to have 180. They can't have 180.2, 181. They can't have 185, 192. They have to be exactly 180. That's how it works. Right? It's impossible to work any other way. In reality, right? You can make it work mathematically, like back here. You can do that nonsense if you want, but that's not reality. So when we move on, we can see again how it would be used for both. You can do it horizontally with a sextant. You can measure if you know the distance between 2 points. You can determine where on land. You can determine where the distance to your boat, or where you are in relation to those points. I'll show you again. Here you have 2 lighthouses and you have a boat, and one is a 50 degree angle here and a 60 degree angle here, and the distance is whatever, 10 miles. Then if you want to know how far you are from those, or what position you're in relation to those two, you're going to use trilateration, right? You're going to use 180 degrees triangle, right? That's the way it works. That's how they can do it with a sextant horizontally, right? Because they don't use it vertically. They can use it vertically, with lighthouses and stuff, with the sextant, but they can't do it with the celestials vertically, because you don't know the height of the celestials. But they can do lighthouses vertically and determine their distance from a lighthouse or something, or a piece of land, when you know the height of it or whatever. But they can also determine their distance between 2 locations horizontally, right? So that's another thing they can do. They can't do that with curved lines and more than 180 degrees or less than 180 degrees. It just doesn't work. In reality, regardless of the size of the triangle, it has to adhere to 180 degrees. Right? It's impossible. This is a triangle. It's impossible for it not to have 180 degrees internally. Now, here we have LIGO. Now, LIGO, I did a thing where I measured along the length of in Google Earth. I made a polygon, right, using the 2 arms of LIGO, right, and a line between them. And what was funny is Google Earth, when I did that same polygon in a right-angled triangle calculator, and the result I got from Google were different, because Google's result treated the adjacent and the opposite exactly the same. So in the right-angled triangle calculator, the opposite and the adjacent, and on Google Earth, the opposite and the adjacent were exactly the same length. But the hypotenuse in Google Earth was shorter. And I thought it was maybe down, because I wasn't a big area, I thought it was maybe down to my accuracy. But then I went on and I did it again, and it was still wrong. There was still a difference. Then I did it with a bigger area, and there was a bigger difference, and a bigger area again 2 more times, and there was a bigger difference 2 more times. And I figured out what was going on. Google Earth, right, what they're doing is they're treating, let's say this is the opposite, this is the adjacent, right? They're treating those 2 sides of the triangle as straight lines, right? But they're trying to give the impression, right, that you're on a spherical convex surface. But the problem with that is, if they do that, right, what happens is the hypotenuse between these 2 points, this adjacent and this opposite, all curve, and they end up with spherical excess. What's that? That'd be like stretching out the land here, and there's a void in here that doesn't exist. So how did they account for that? What Google Earth does is they shorten the hypotenuse, which is mathematically impossible, right? It's mathematically criminal, geometrically criminal to do that. But they shorten the hypotenuse while still visually giving you the impression that you are dealing with what they call an oxymoron spherical triangle. But really what they're doing is they're giving you the impression of it, but then mathematically they're taking away they're taking away that spherical excess, because in reality it doesn't work. It doesn't exist in reality. That's why it's called spherical excess. because you're after adding in surface area within those 3 lines that doesn't exist. That's what they do. So Google Earth hides the spherical excess by shortening the hypotenuse. So how can you have a shorter hypotenuse if this is treated as a straight line and this is treated as a straight line, especially because it's LIGO, right, by Google? Then how is it possible to have a shorter hypotenuse than what you would get in a right angled triangle calculator? And it wasn't just, I also did this without LIGO. I also did it using coordinates, and Google Earth still treated the opposite and the adjacent as straight lines, but it shortened the hypotenuse. Why did Google Earth shorten the hypotenuse? It's very simple, because Google Earth knows, right, or the developers of it know, that when you curve those lines, right, you create spherical excess. But spherical excess doesn't exist in reality, and neither does curved triangles. So how did they make up for it mathematically? Every time you do a polygon, you have a shorter hypotenuse than you do in reality. What a farce. Spherical excess is absolute nonsense. It's a total farce. It doesn't exist. There is no spherical oxymoron triangles in reality. None of this happens. It's all mathematical. It's all a farce. It's all there to help you, keep you believing that you live on a globe, or some of this stuff is measured. If it's measured, then you're going to have a measured R value, because that's the first thing you're going to need for any of this nonsense to even start. Before you can even talk about anything, you're going to need a measured R value. Something that doesn't exist, has never existed, and it never will exist, because we don't live on a globe. It's that simple. The Earth's not a globe. Triangles don't have more or less than 180 degrees. Nobody measures triangles with more or less than 180 degrees. Spherical excess doesn't exist. Google Earth are liars, and geodetic surveying are liars. End of. Thanks for watching.